Good afternoon, everyone. Welcome back. I hope that you guys had a really fantastic break away from everything. It's been a while since we've learned any new material. A full week, in fact. So today we're moving on. We're looking at lesson 30.15, and this can be found on page 1 of the new lesson handout. So this lesson handout is part 3, and it is the final handout. What we're looking at today is something called the deBroglie wavelength. And a fellow by the name of Louis de Broglie, a French physicist, there he is, very happy looking fellow, asked the following question. He said, if photons can behave like particles, which is what the Compton effect and also the photoelectric effect demonstrate, if it's possible for photons which have no mass to have a property like momentum, which is traditionally thought of as a property reserved for particles with mass, then is it possible for a real particle, that means a particle that actually does have mass, to behave like a wave? So if photons, which are waves, can behave like particles, what de Broglie is asking is it possible for particles which have mass to behave like waves? So what he did was he took the formula for momentum of a photon that Compton developed, and he rearranged it for wavelength, and it becomes wavelength equals Planck's constant over momentum. Now de Broglie is interested in particles that actually have mass. So since the mass times the velocity gives you the momentum of an actual particle, we can put into the formula lambda equals h over p, we can put in for p mass times velocity, and we get this formula, lambda equals h over mv. By the way, this formula is not on your formula sheet. And this is what's called the de Broglie wave hypothesis. His hypothesis, he believed that particles that actually had mass when they were moving behaved like waves. Now, we're not going to explain right away what that means to say that something like a proton or an alpha particle or an electron can behave like a wave. I'm going to explain that in a little bit. We're going to start off by calculating the de Broglie wavelength of two different objects. One is a car, and it's a fairly small car. It has a mass of 1,250 kilograms, and it's traveling at 30 meters per second. And then the other particle is an electron, and it's traveling at 2 multiplied by 10 to the 6 meters per second. So it says compare the two de Broglie wavelengths and use them to explain what a de Broglie wavelength means, and also explain why we would never ever be able to observe evidence of a de Broglie wavelength of a macroscopic object like a car. So how do we go about doing this? Well, we start off with what I'm going to refer to from now on is the wave-particle duality formula. Right now, this formula for wave-particle duality is revealing the particle property of a wave side of the formula to us. In this form, it can be used to calculate the momentum, which is a particle phenomenon, of a photon which has no mass. If we turn this equation over, we flip it over, it becomes the wavelength equals Planck's constant over momentum. And now what this formula is showing is the wave side of wave-particle duality. This is how we calculate the wavelength of a particle with mass, and we can take it one step further, as we've already talked about, and use mv for momentum. So for me to calculate the de Broglie wavelength of this car would mean I would take Planck's constant, which is 6.63 multiplied by 10 to the negative 34 joule seconds. I need to divide that now by the product of the mass, which is 1,250 kilograms, and the speed, which is 30 meters per second, and that's going to give me the de Broglie wavelength of the car. To calculate the de Broglie wavelength of the electron, we take Planck's constant, we divide by the product of the mass And the speed? Well, the mass of an electron is 9.11 multiplied by 10 to the negative 31 kilograms times the speed, which is 2.0 multiplied by 10 to the 6 meters per second. So let's see, 6.63 multiplied by 10 to the negative 34. We have to divide by the product of the mass and the velocity. So I'm going to put a set of brackets here and take 1250 multiplied by 30. And we get a deBroglie wavelength of approximately 1.8 multiplied by 10 to the negative 38 meters. We do the same kind of calculation for the electron and get 6.63 multiplied by 10 to the negative 34 divided by the product of the mass and the velocity, 9.11 multiplied by 10 to the negative 31 multiplied by 2 times 10 to the 6. And for a deBroglie wavelength of the electron, we get about 3.6 times 10 to the negative 10 meters. Now, why is it that we would never be able to observe wave-like behavior of a car? Well, the two phenomena that really indicate that a source of energy is a wave are diffraction and interference. Remember that when a wave passes through an opening, the wave energy spreads out. And if you were to pass that wave through two openings, the wave will spread out as it leaves each of the two openings and you get an interference pattern. So diffraction and interference really tell us that something is a wave. However, in order for diffraction of a wave to occur, the size of the opening has to be smaller than the wavelength. Now, when you take a look at the wavelength of the car, it's in the order of 10 to the negative 38 meters. And the fact of the matter is there's no opening in the universe, natural or man-made, that can be constructed to be that size or smaller. And by the way, even if you could construct an opening that size or smaller, you can't fit the car through the opening. So that means that if this deBroglie wavelength idea is true, the deBroglie wavelength of a car is just too small to be meaningful in any way. On the other hand, when you take a look at the size of the wavelength for the electron in our example, it's in the order of 10 to the negative 10 meters. And there are natural spaces in crystals that are about that size or smaller. And it was discovered shortly after deBroglie made this hypothesis that when you fire a beam of electrons at a crystal in the right circumstance, what you will get is a diffraction pattern. You will get evidence of interference. And without going into a lot of details, because we've had to cut a lot of corners in the rest of this course now, we have seen direct evidence for diffraction and interference of electrons, which means when you pass electrons through an opening a little bit smaller than that wavelength that the electron has, the electrons diffract and the electrons interfere. So now what I'm going to do is I'm going to explain to you what that means when we say electrons in this situation diffract and interfere. But in order for me to explain this to you in a meaningful way, I have to go back and talk about how waves diffract and interfere. So to begin with, when you have a single opening and a wave passes through that opening, we know that the wave spreads out. This is called diffraction. And what you end up seeing on the other side is a distribution of energy. Remember that the peak energy occurs opposite the opening, and as you get further away from the opening on the left and the right, you get less energy. You still get some energy, but not as much. So again, if this were a sound wave and you were walking from left to right at the bottom of the screen, the level of sound that you hear would start off low, and then it would increase to a maximum value, and then it would start dropping off again after you pass that point directly across from the opening. It's no surprise that if I open up the other opening, then you get the exact same thing happening. That is to say, you get a distribution of energy that's spread out because the wave diffracts. We know that waves diffract. When you have the wave passing through the two openings, common sense would say that since you get a peak of energy observed across from the left opening when it's open, and you get a peak of energy across from the right opening when it's open, that you should get two peaks of energy, but you don't get that. We have already learned this. You talked about it a little bit in Physics 20, and we went into greater detail in this course when we talked about Young's double slit experiment with interference of light. What you get instead is this distribution of energy that's an interference pattern, and you have the maximum interference occurring directly opposite the center of the openings, and as you move to the left or to the right of that central maximum, you encounter other maxima and other minima, and the intensity of the maxima decrease as you go out. The n equals 1 has less energy than the n equals 0, the n equals 2 has less energy than the n equals 1, and so on. So that's waves and how they behave when they pass through two openings. Now let's talk about particles, and I want to bring your attention to the fact that in the top of the screen I'm saying these particles are behaving like particles. So what are we talking about here? We're talking about things like golf balls or marbles or rocks. And if I fire a whole bunch of these particles downwards from the top of the screen towards the opening, you're going to get some of them bouncing off of that barrier and not making it through, but you're going to get some of them making it through. And you're going to get this little pile of pebbles or marbles or whatever it is that these particles are. And that means that you get a distribution of energy. Now, by the way, the energy is spread out a little bit here, not because these are diffracting, but because the size of the opening allows these objects to kind of fall into a spread. They don't land exactly in the same place every time. And if I were to allow the particles to move through the second opening, I would get the same thing. So you would get a pile of energy directly across from the opening. And if I open both of the openings, so you can imagine this is like a concrete wall with a couple of openings, and you're randomly throwing a whole bunch of rocks at the wall in different places, what you're going to discover is you would get two piles of rocks, and that would mean you would get two piles of energy. And in fact, that is what we observe as long as we're talking about things like golf balls or marbles or cars or oranges, things that I would describe as being macroscopic, large. Now let's talk about particles behaving like waves. So again, I'm drawing your attention to the top of the page where we have the phrase particles behaving like waves. So at the bottom of the screen, I'm saying these are things like electrons or protons or individual molecules. The important point here is they're very tiny. If I open up one of these openings, then these tiny, tiny particles behave exactly like golf balls or marbles. They will pile up in one place, giving a distribution of energy. If I open up the other opening, the same thing happens. So when we open up one of the openings, whether it's the left or the right, these particles, and make no mistake about it, electrons, protons, atoms, and individual molecules are particles. The only thing that makes them different than a golf ball is these particles are really, really tiny. But when we open up either of the openings, these things behave like particles. However, if we open up both openings and we fire the particles through, Common sense would say you would get two piles of particles. However, common sense is wrong in this situation. That is not what happens when you open up both openings. What happens is you get this, which is an incredibly surprising result. You end up with piles of the particles in different locations that collectively form an interference pattern. And this is one of the strangest things in physics to wrap your head around, because these particles are moving through one at a time. So we get what we call an interference pattern, but each particle moves through on its own. So it has nothing that it can interfere with. If I fire one particle through, say at 12 o'clock on Tuesday, and I observe where it lands, it might land there. I come back a week later and I fire a second particle through, and it lands there. And I come back a week later, and I continue to do this. And they continue to land in these seemingly random places. And I continue week after week, or minute after minute, or decade after decade to come back into this room and fire these particles, these electrons, or these really, really tiny particles. And they continue to pile up, producing over time an interference pattern. And this should not sit well with you. You probably are not going to be looking at this and going, well, yeah, that makes sense. Because it doesn't make sense. Nothing about this makes sense at all. And it gets even more bizarre. So now what we have is the same experiment, and we have an electron detector. We have some way to decide whether a particular electron goes through the opening on the left or the opening on the right. But if you take a look at the electron detector, it's connected to a potential difference, and there's a switch near the bottom of your screen. The switch is open right now, which means the electron detector is turned off. It's pointing at the openings, but it can't see the openings until I turn the switch on. Right now, we get an interference pattern. As soon as I turn the electron detector on to take a look at which electron goes through which opening, the interference pattern goes away, and these electrons behave like perfectly sensible particles. So as soon as you start observing which opening the particles go through, the particles fail to interfere and produce an interference pattern, even though they're only going through one opening at a time. There's another very, very weird result to this experiment, and it's that you have the experiment set up to randomly fire through either the left or the right opening, but you've also got it set up so that if the random event is through the left opening, the right opening is closed. And as soon as you have the electrons going through one opening and the other opening is closed, they don't interfere. If, however, you have the electrons going through one of the openings, but at the same time the other opening is open, the opening that the electron does not go through is open, then what you get is an interference pattern. This is one of the true mysteries of the universe, is what's going on here. The deBroglie wavelength, though, is something that we have found evidence for. So when there's nothing observing which openings the electrons are going through, you get a beautiful interference pattern. As soon as there is an observer, the interference pattern disappears. I don't want to leave you with the impression that there's something mystical going on here. What's going on fundamentally is that in order for you to observe an event, you have to make contact with the object. In order for me to pick up my coffee cup, I have to see light reflecting off of it to know where the coffee cup is. So in order for me to see where the electron is, I have to hit it with electromagnetic radiation. It appears as though when electrons are nudged with electromagnetic radiation so that we can see them, their wave nature disappears and they turn into a particle. Okay, so let's take a look at example 2. Electrons are accelerated to a particular speed, and the electrons are directed to a crystal which acts as a diffraction grating, and the distance between the atoms in the crystal, which is d in an interference formula, is 7.2 multiplied by 10 to the negative 9 meters. You're asked to determine theta for n equals 1 and theta for n equals 2, and you're going to do that by using Young's double slit formula, lambda equals d sine theta over n. This is exactly the same type of thing we did in the assignment where we were determining the wavelengths of the lasers using diffraction and interference. Except we were talking in that assignment about diffraction and interference of light. In this example, we're talking about diffraction and interference of electrons. When you take a look at what we know, you know d, it's given to you, and we know n. What we're missing in order for us to find theta is the wavelength. But that's okay, we can calculate the wavelength using the de Broglie wavelength formula. So if we take Planck's constant divided by the product of the mass and the speed, we will get the de Broglie wavelength. So the de Broglie wavelength is Planck's constant over the mass times the speed, which gives me a wavelength of 2.079 multiplied by 10 to the negative 10. And now what we can do is use that wavelength in Young's double slit formula, lambda equals d sine theta, to find out what theta is for both of those n values. So for the n equals 1, we are going to have the wavelength being equal to d, which we know is 7.2 multiplied by 10 to the negative 9 meters, times sine of the angle, which is what we are after, divided by n, which is 1. And for n equals 2, we're going to have the exact same formula. But this time it will be over 2. So it looks like in order for us to find sine theta, I have to take that wavelength and divide by d, which is 7.29 multiplied by 10 to the negative 9. And then I have to take the inverse sine, making sure I'm in degrees, which gives me about 1.6 degrees. So for the n equals 1, it's 1.6 degrees. For the n equals 2, well, I have to do the same calculation. I have to take the wavelength and divide by d, which is 7.2 multiplied by 10 to the negative 9. But then I have to multiply by n, which is 2, and then take the inverse sine. And I get for the n equals 2 about 3.3 degrees. So the answers to this question is that the angle to the n equals 1 maximum is about 1.6 degrees, and the angle to the n equals 2 maximum is about 3.3 degrees. And that's example 2. Example 3 takes us a little bit further down the path. It's pretty much the same kind of idea here. You have the formula for the de Broglie wavelength, lambda equals h over mv. You have the formula for double slit interference patterns, lambda equals d sine theta over n. But we go back a little bit further to how the electrons got the speed they had, which gave them the de Broglie wavelength that they had. And that's that they were accelerated by a potential difference. So we are also dealing with change in energy divided by charge is equal to potential difference. This formula here, by the way, we have used numerous times in this context. When you cross multiply, you get 1/2 mv squared equals q delta v. So what is it we need to do here to find the voltage? If you look at the formula on the left, the thing that we are missing is we do not know the speed of the electrons. So that's the goal. If we can determine the speed, then we can determine the voltage. When you look at the middle formula, the only way we could find the speed is if we knew the wavelength, and we don't know the wavelength. We're going to use the formula on the right to determine the wavelength first. Then we can use the wavelength with the formula in the middle to determine the speed. And once we know the speed, we can use the formula on the left to determine the voltage. I'm not going to write down a whole bunch of numbers here. I'm simply going to write down the formula rearranged for what we want. While in the first case where we want to calculate lambda, it's already rearranged for lambda. In the second formula, the middle formula, when we cross multiply and divide, we get h over m lambda, which would give us the speed. And then in the third formula, of course, we can take 1/2 mv squared divided by the charge to get our final answer of the voltage. So we're going to calculate the wavelength, then we're going to calculate the speed, then we will have the voltage. All right, the wavelength is d sine theta over n. D is 5.2 multiplied by 10 to the negative 10 meters. We need to multiply that by sine of the angle, which is 11.5 degrees. And we need to divide that by n, and it says it's the second order antinode. So that's the second maximum, which means n is 2. When we do that, we get a wavelength of 5.18 multiplied by 10 to the negative 11 meters. And now we can use that de Broglie wavelength in the de Broglie wavelength formula to find the speed. All right, so now let's calculate the speed that the electrons have. We have to take Planck's constant, 6.63 multiplied by 10 to the negative 34, and divide by the product of the mass. It's an electron, so it's 9.11 times 10 to the negative 31, multiplied by the wavelength, which is my last answer on the calculator, and what I am getting is this speed, 1.40 times 10 to the 6 meters per second. If I take that speed and calculate the kinetic energy by taking 0.5 times the mass, times the speed squared, This is the change in energy of the electron when it was accelerated, but voltage is change in energy over charge. So I need to divide this by the charge of an electron. I'm using the formula on the left, which is giving me a final answer of 561 volts. And that's the answer. So there's kind of two levels to this lesson. The first one is that you know how to calculate the de Broglie wavelength. You start by taking Compton's formula for the momentum of a photon. You rearrange it for wavelength and get h over momentum. And then you say that for a particle that has mass, its momentum is mv, and you've developed your formula for the de Broglie wavelength. In other words, the first level in this lesson has to do with your ability to calculate a de Broglie wavelength. The second aspect of this is understanding what this means, and all it means is that under the right circumstances, these particles that have de Broglie wavelengths, when they pass through openings, will produce an interference pattern on the other side. You can see what the assignment is. I don't think in the handout I even said which numbers. There are 8 questions there, so the assignment is questions 1 through 8. Tomorrow is a Google Meet day, so if you have any questions with this or anything else that you've been working on that you need help with, show up. And if you can't make it to the Google Meet, my email offer is always there. If you have a question, send me an email anytime, and I will get back to you as soon as I can. I hope that made sense, and I hope that you have a fantastic rest of the day, and I will talk with everybody soon.